Similarly, let us consider another structure is there which have a hole, inner hole. So, for this case also you see this, there is a, due to this inner hole, let us consider it is subjected to a force F. Then for this case also, once we go for calculating the nominal stress, let us consider the inner hole diameter is small d and capital plate width is W. So, for this case once we go for calculating the nominal stress, here we should consider the effect of this what is called inner hole. So, how we consider these things? That is generally a stress rising effect, that you can say. So, for calculating these things, generally the definition of nominal stress is F divided by, you can say, let us consider the thickness of the plate is, let us consider the thickness of the plate is T, thickness of the plate is let us T. So, for that case we can say here we should consider W minus D into T, this you should keep it in mind. So, here also we consider the effect of this inner hole of this plate, that is why we have considered the minimum effective dimension of that plate. Here the minimum effective dimension due to cut off hole is W minus D into T, that things we have considered. So, that points here I have written. The stress rising effect of the geometrical configuration or irregularities of the main component for calculating the nominal stress we should include, this you should keep it in mind. The nominal stress method generally requires, I have already told you the fatigue classes, what is fatigue classes, that also I will discuss in subsequent slide. And that is that fatigue class or also it is called fat SN curve, which can be found in some design code as well as some guidelines are there generally it is available. We can use those data once we go for using nominal stress approach. So, in case of more complex geometry where this fatigue class data or SN curve data is not available, there generally this nominal stress approach is generally we avoid to use, this you should keep it in mind. So, for those types of complex geometry it is better to use some other fatigue life estimation method. Now, what are the steps generally we use in nominal stress method, that I am going to discuss. So, first step of nominal stress method is, first we need to calculate the nominal stress sigma NOM, you can say. This sigma nominal stress we can calculate by some elementary theory of mechanics or by some numerical method like finite element method. FEM means finite element method, this you should keep it in mind. Okay. Finite element method is a numerical method or is a approximate method. It is very popular method. Generally nowadays different finite element software are available. Those software we can use to estimate this nominal stress. Some of the software name I am just telling, like ANSYS software you can use, Abacus software we can use. These are all, then COMSOL software, Neston software, these are the all different types of what is called finite element based, you can say software packages. This software generally we can use to estimate the nominal stress value, as well as if the geometry is very simple, there we can use some elementary theory of structural mechanics, which I have already shown in previous slide, like a plate with a hole. For calculating the nominal stress directly we can use F divided by W minus D into T, thickness of the plate. These are all generally elementary theory of structural mechanics. That means this is the first step, you can say. First step is calculating the nominal stress. Then the second step is calculate the FAD value. FAD value means fatigue strength value according to the standard, because I have already told you this FAD value is, what is FAD value in details I will discuss in subsequent slide. FAD value, generally there are some standard SN curve data. In this standard SN curve data is estimated based on some standard well geometry, and that is plotted in what is called stage versus number of cycle plot, and from there generally what happens, at a value of 2 to 10 to the power 6 cycle, what is the what is called stage value is there, that stage value is called FAT or fatigue strength value. So, what is FAT value? FAT value is for different well geometry, different SN curve is there. For a particular types of welding configuration, we got a SN curve. From that SN curve, generally for a number of cycle of what is called 2 into 10 to the power 6, whatever the stage value we will get, that stage value is called FAT value for that welded geometry. This you should keep it in mind. So, in subsequent slide in more details we will discuss about this FAT classification. And finally, step 3. So, nominal stress and FAT value we calculate, and finally we need to calculate the fatigue life N with the help of this following equation, like 2 into 10 to the power 6, this FAT divided by sigma nominal stress, that means FAT strength or fatigue strength divided by nominal stress to the power N. Okay. By using this formulation we can calculate the fatigue life. What is N? N is the slope of this SN curve. This you should keep it in mind. Now, one by one we will discuss these different steps, then it will be very clear to us. So, first is calculation of nominal stress. So, the calculation of nominal stress can be done in two way. So, the one method is by using elementary theory of structural mechanics, which is based on linear elastic behavior for simple component, which I have already told you. This is one method. The another method is by some numerical method like finite element method. This finite element method generally we use when the geometry is complex in nature, and this complexity is such which is generally statically over determined structure, or you can say the structural component incorporating macro types of geometrical discontinuity. For this case generally this finite element modeling method we use to calculate what is called nominal stress value. This you should keep it in mind. Now, first of all I will discuss about calculation of nominal stress using elementary theory of structural mechanics. So, elementary theory of structural mechanics, how it calculate the what is called nominal stress, that I am showing. So, this I have already told you this this elementary theory of structural mechanics generally used for simple component, and so nominal stress is the average stress in well throat or in the plate at the weld toe, you can say. How generally this nominal or average stress we can calculate, that I am showing. So, for calculating these things, a parameter A is required to determine. The parameter A is determined differently for different joint, which I am showing here, like what happens for bar joint. For bar joint generally what is called this A is calculated one way. You can call as what is called if the in case of bar joint generally if dissimilar joint plate is there, then for bar joint generally this A is considered as minimum thickness or lower thickness plate thickness. This you should keep it in mind. Now for what is called fillet types of weld joint, generally this A is considered as what is the from root of the weld to face of the weld, that means minimum distance between root to face of the weld. So, we know these things, what is root, what is face. I have already told you in case of fillet weld, this is generally called face of the fillet weld, this is called joint root. If welding is done, they are generally weld root, if there will be some fusion of this is there. So, this point is called weld root. So, from this weld root to minimum distance from what is called, or you can say perpendicular distance from this face to this weld root is called generally A in case of fillet weld. So, this parameter is a very important parameter. For simple geometry we can easily use. So, for this generally in case of butt weld, where let us consider two dissimilar thickness of the plate are there, let this is one plate, another plate is, let us consider this. So, here let us consider we did the butt welding. Okay. So, let us consider here the thickness is T1 and here the thickness of the plate is T2. So, for this case let us consider it is subjected to a load F, axial force let it is subjected. So, for this case here the nominal stress calculation will be F divided by, you can say AW. AW means welding zone cross sectional area. What is AW? AW you can say F divided by what is called, in case of dissimilar thickness, here AW will be T2 into length of the weld. LW is called, here I have already written, here LW is called length of weld. This you should keep it in mind. So, this way generally we can calculate for butt weld, what it is called, we can calculate this nominal stress. If the thickness of the plate is same, then there we can use what is called T into LW, both the thickness is same, there we can use this T into LW. But for fillet weld, generally in throat area, there occur generally, let us consider shear stress. So, here the shear stress we can write as F divided by throat area, weld throat area. So, here generally F divided by A into LW. What is A? I have already discussed. A is the distance from root to face of the weld, minimum distance from root to face of the weld, that you can say, or you can say perpendicular distance between root to face of the weld. This you should keep it in mind. So, this way you can easily calculate the what it is called nominal stress value if the geometry is simple. But if the geometry is complex in nature, for complex geometry generally calculation of nominal stress is done by using finite element method. This is a numerical method. So, here generally we need to do the modeling first. So, this finite element method means first we need to discretize, or you can say mesh the structure into finite number of element. After that generally we need to apply the boundary condition, joint geometry and all the things. So, after that whatever the, once we do the analysis, we can get the stress distribution throughout the entire welded structure. So, for this, once we generally you see, once we plot the stress distribution from here I have shown one example. So, for these types of welded structure, if we just calculate the stress distribution from weld toe, let this is your weld toe to away from the weld toe zone, then we can get that okay, the stress distribution is varying like this. So, if it is come closer to weld toe, the stress magnitude is gradually increasing. if it is but far away from far away in the sense at a distance of around thickness of the plate, from there onwards you can say the stress distribution more or less uniform in nature, if the load is applied axial types of load. If it is bending types of load, then this stress distribution will be different. So, for this case generally what we need to do, generally for this case we need to generally calculate the nominal stress by extrapolating this linear region stress towards the what is called torque zone. After extrapolating whatever the point of this linear zone cut at a toe region, at that region whatever the stress value we will get, that stress value is generally called nominal stress for this well toe. This you should keep it in mind. So, how we calculate? This is very simple. You can say the linear stress zone we need to extrapolate, and we need to extrapolate towards welding zone, and it should extrapolation line should extend till well toe zone. So, at this well toe zone wherever this stress value will cut, at that location whatever the magnitude of stress value will get, that value is called nominal stress. So, that things here I have written. You can say to find out the nominal stress in FEM model, a plot you can say is created of the stress along a path approaching the weld. That means along a path approaching the weld, that you can say approaching the weld. So, the FE model often has a gradient near the weld that corresponding to the geometrical stress. So, what we observe, that means after certain once we come close to weld zone, there we will observe the stress value is increasing, start increasing. That means there start occurring stress gradient. This means stress changing with distance, that is called gradient. Okay, that things only here we have written. So, the FE model often has a gradient near the weld that corresponding to geometrical stress. So, a simple rule to obtain the nominal stress is to extrapolate the linear part. These things you should keep it in mind. But for hot spot method, I have already told you, there is we need to decide 2 points. One is generally at a distance 0.4 t and at a distance 1 t. After that we need to draw a straight line, that line we need to extrapolate. But here the linear part of the stress on the surface, generally that we need to inwards against the weld. If we inwards against the weld, where it's cut at weld toe zone, at that location whatever the stress value will got, that is generally called nominal stress. This you should keep it in mind. Here that linear part we need to extrapolate towards what? Weld. This you should keep it, that is generally called nominal stress. Here I have shown. Okay. Now, nominal stress at weld root, how we can calculate, that also we need to know. So, this is weld toe zone, how to calculate nominal stress, that I have already shown both for butt weld as well as both for simple geometry as well as complex geometry, which are at weld toe zone, how to calculate the things that we have discussed. Now, nominal stress also we can calculate in what is called weld root zone also. So, how to calculate this thing, that I am just going to discuss. So, when the weld is sensitive to fatigue root cracking, that means if the weld cracking is sensitive at root zone of the weld, at that time generally what happens, we need to consider the nominal stress at weld root position. That is why I have written, for that case the analysis should be based on stress at the weld throat by calculating the weld stress sigma NW. That means at this weld throat zone, whatever the stress value will be there, that stress generally we need to use for estimating the fatigue life once the crack can be started at weld root zone. This you should keep it in mind. So, at weld root, what is weld root? I have already discussed for fillet weld. What is weld root? I have already discussed. So, for weld root fatigue life estimation or weld root nominal stress calculation, what we need to consider? We need to consider the throat zone. Throat zone, what is throat zone? I have already discussed. Throat zone, this is called throat thickness. Okay. So, once we consider failure in weld root, in that case nominal stress we need to calculate at this throat zone. So, in this throat zone, the whatever the nominal stress will be there, that is generally represented as sigma NW. Why sigma NW? Because here the nominal stress we are calculating in welding throat. What I am telling, understand? Whereas in for toe zone, generally nominal stress we calculate, you can say, at the base material zone. This you can say, where the you can say stress distribution is uniform throughout the thickness, that you can say. But if we want to calculate what is called throat nominal stress, where throat nominal stress in the sense, if the failure is happen in root zone, so this weld nominal stress is the stress which is at weld throat zone. This you should keep it in mind. So, how to calculate this sigma NW, that we need to know. So, for calculating this sigma NW, here what happens, let us consider this is a cruciform types of weld. Cruciform types of weld means, you see here 4 fillet weld is there and you can say 2 perpendicular plate are there. You can see 2 perpendicular types of structure components are there. So, here you can see in this throat area how the stress distribution is look like. So, in this throat area, one of the stress component will be normal stress component, another stress component you can say this is, let us consider average normal stress component, and average normal stress component I am writing, let us consider sigma inverted T, okay. And here there can be a shear stress component, different color I am using, that will be better. So, let us here there will be shear stress component. So, there will be a normal average normal stress as well as in this weld throat area there will be a shear stress component that I am representing tau inverted T. So, these 2 component will have a resultant component, that resultant component is called throat nominal stress. This is called throat nominal stress. This throat nominal stress generally is used for what is called calculating the fatigue life once the what is called root crack is taken place. This nominal stress is used there to calculate the fatigue life using nominal stress approach. This you should keep it in mind. So, how to calculate this nominal stress? So, what happens in this throat area, we are getting one normal component stress and one shear component stress. So, normal component stress will be perpendicular to the throat area and shear component will be along the throat area. So, these 2 component will have a resultant component. Here I have already shown, let this is our sigma inverted T and this is tau T. So, this resultant component is this. This resultant component we can easily find out, that is actually a square root of this normal component square plus shear component square. By using this we can easily calculate this sigma NW. So, this sigma NW also we can relate with what is called normal nominal stress at what is called plate zone. What I am telling at plate zone in the sense what is called away from the weld zone, whatever the nominal stress we get, that way also we can correlate. Like little bit here I am just showing this nominal stress sigma NW into whatever the what it is called, let us consider here in case of cruciform weld, here one throat is there, here another throat is there. So, here generally two throat is responsible for carrying the load F. So, that is why what happens here you can say sigma NW into 2A into length of the weld, this is the cross sectional area. So, whatever the force will be there, this force is equal to your whatever the applied force F is there. This applied force F we can write as what? This applied force we can write as nominal stress at this plate, here I have shown, into what is called thickness of the plate. Let us consider the thickness of the plate is T, thickness of the plate is T here, and this LW, length of the weld. So, if we equate this thing, what we are getting NW, this LW cancel out into 2A is equal to sigma N into T. So, here sigma NW also we can calculate with the help of this nominal stress at plate thickness sigma N into plate thickness divided by you can say 2A, where 2 throat thickness is responsible for carrying this load F. This you should keep it in mind. Whereas, if both side butt weld is there, for this case also let us consider this is F is there. So, here also sigma NW into 2 into A, let us say the throat area is here, from here to here, both side here this 2 throat area is there, sigma NW into 2A is equal to you can say sigma N into T. So, from here also you can say same relation, sigma NW you can calculate the same relation if it is both side welding is there. This way generally we can calculate sigma NW in terms of nominal stress. So, once the root area is considered for fatigue cracking or fatigue failure zone, then what happens, to estimate the fatigue life at root we need to consider nominal stress at the weld throat zone sigma NW. There we need not to consider sigma N value, whereas at weld toe zone we can consider what? Weld nominal stress as sigma N only, that is the weld plate thickness which is average stress for the plate. This you should keep it in mind. So, here I am writing for weld you can say toe sigma N is used, this you should keep it in mind, and for weld root sigma NW is used. This you should keep it in mind. Now, relationship between sigma N and sigma NW also I have shown. Okay. Now, one of the example I am showing just how this what is called NW sigma NW is coming. Let us consider what is called a weld. Let us consider this weld, little bit I am showing. Okay. This is on fillet weld and this is another fillet, this side another fillet weld. It is subjected to a load F, a force F. For this case generally what we need to consider, this throat area and this throat area. So, here let us consider this fillet is isosceles triangle. So, in case of isosceles triangle we know this fillet generally this throat generally makes an angle alpha with the what is called horizontal axis, that is 45 degree. This angle will be, you can say, 45 degree. Okay. So, here generally this normal component of the stress we can calculate as what is called F divided by this, and for tau component generally we can use F divided by 2 into A LEF. For these types of weld joint, generally how to calculate normal stress and what is called shear stress component, that I am going to show. So, here you see, in this case this is the normal stress, this normal stress we need to calculate. Okay. So, this for calculating this normal stress, this sigma inverted T and tau inverted T we need to calculate. So, sigma T, how we can calculate? Sigma T we can calculate as directly here I am showing sigma T into 2 into A into L effective. This force should be equal to F sin alpha. This you can see, because this normal stress component which have a angle, you can see here it is, here you see this is the alpha angle, this alpha angle generally makes with this horizontal axis, with this throat area, throat, or you can say throat line, this alpha angle is made. So, you see, so the throat area we can write as 2 into A into L effective. Okay. This is the throat area. Why this 2A we are considering? Because you see this one A here, another A here. So, this two throat area, or you can this two throat generally responsible for supporting this load F. That is why here 2A we are considering. And let us consider the effective length of the weld is L effective. So, sigma T into 2A into L effective will give us a force. This force component should be equal to whatever the normal force is there, this is the axial force is there, this axial force, this component, it should be balanced with that normal component. So, this force will be what? Sin alpha. Why sin alpha? Because generally the throat zone, this is the throat zone which makes an angle alpha. Okay, that is why this is sin alpha, but for shear component this will be cos alpha. If alpha equal to 45 degree, then what happens? Sin alpha equal to cos alpha, that will be there. So, how this is balancing, that idea you got. So, from here what we can, this is generally you can say equilibrium of equation, that means summation of, you can say x component of force should be equal to 0. Similarly, summation of y component force equal to 0. These are all based on equation of equilibrium. So, based on this thing generally this relationship is come. So, from here sigma inverted T normal component we can write as F sin alpha divided by 2A L effective. Okay. Similarly, for what is called shear stress component, here this will be F cos alpha. Okay. So, this shear stress component, due to the shear stress, what is the force we will get? This force we will get will be, you can say, tau T into what is called 2A into what? 2A into L effective, correct? This is the force along the shear plane. This force will be balanced by F cos alpha. So, you can write like this force balance equation for this shear stress component. What we can write? Tau inverted T into 2A into L effective, effective means length of the weld, effective length of the weld. this should be equal to what? F cos alpha. This alpha, which angle, everything I have shown. So, from here generally you can write as tau t equal to this. Now, if alpha equal to 45 degree, then cos alpha equal to sin alpha equal to cos 45 degree equal to, you can say, 1 by root 2, that we know. So, that things once we put, then we got sigma t and tau t equal to this value. If sigma inverted t and tau value, that means normal stress and shear stress value is this, then we can easily find out what is sigma n w. Sigma n w is a square root of sigma inverted t square plus tau inverted t square. Just put these things, what we will get? We will get F divided by 2A L effective. So, where A is called throat thickness, and L effective is called effective length. Since L effective is a very important parameter, here one thing you should keep it in mind. If the throat thickness is, this throat thickness means if this A is less than 5, then always you should keep it in mind, this L effective should be at least 30 millimeter. But if the throat thickness A is greater than 5, for that case generally L effective should be equal to 6 into throat thickness, where A is greater than 5. If it is less than 5, for this case minimum we should consider L effective equal to 30 millimeter. This you should keep it in mind. This way generally we can calculate what is called sigma n w. Sigma n w we can calculate. This sigma n w is now known to us. So, and sigma n also for simple geometry how to calculate, that is also known to us. For toe fatigue life estimation, that is also known to us. Now, in next lecture I will discuss how to find out what is called fat value. After that I will solve some problem on nominal stress approach, then our concept will be very clear. So, thank you.